Topological analysis that I'll be talking about is more using pictures. And if it's not rigorous enough, or if you have any more suggestions, please do let me know. So what are grain boundaries? And why do we care about them? Before I talk about boundaries, I would like to introduce what is called as the crystalline state of matter. Most solids exist in this state called crystalline state, where the building blocks basically arrange themselves in an orderly pattern, and this pattern obviously has different symmetries to it. You imagine an infinite system. You could rotate, for example, the hexagonal, the atoms in that hexagonal lattice, and then by 60 degrees, and it still remains the same. So you have rotational symmetries. You could translate them by a unit lattice vector, and it still has the same system. That's kind of a symmetry, and these are the kind of symmetries that are present in the crystals that exist in nature. And there has been a huge amount of group theory analysis in trying to understand what kind of symmetries are present, and it's a finite number. And I'll be talking mainly about the rotational symmetries that are present, and this is how in material science we try to denote these symmetries, the point group symmetries. So the rotational symmetry of a crystal, we talk about the point group symmetry is basically the operations that leave the origin fixed, and there exist 11 crystallographic point groups that crystals in nature can exhibit. And depending upon the point group symmetry, they also take different crystal structures. But so, for example, a C2 point group symmetry is nothing but if you rotate the crystal along its z-axis by 180 degrees, it remains the same. And this is how we show it. There are also the octahedral point group symmetry, which we call 432 in our notation, 4 representing a four-fold rotational symmetry along the z-axis, and the 3 representing a threefold along the 111, and the 2 representing a twofold axis along the 110 crystal direction.
Point out the picture on the left is like a top view of a two-sphere.
Yep. So
mathematicians aren't used to that picture.
Yeah. So the way we represent here is we take one point and then we try to apply all the symmetries to that point, which is on the sphere, and then project it on 2D. And these are all symmetrically equivalent points. So these are the 2 point groups that I'll be talking about later in my talk as well. So I kind of represent them here. And as I said, materials in solid state mostly exhibit this crystalline, exist in crystal state. But where do boundaries and grains come from is because it's very difficult to manufacture single crystal materials. So most materials, even though they form crystalline in crystal state, they form in this structure which is called a polycrystalline material, because the material has different crystals that adjoin and form grains and grain boundaries. And shown there, for example, is a brass door, and they actually have big enough grains that over time, when the grain boundaries selectively corrode, you could see the grains in there, if you can see them. But if the picture is big enough, you could probably see it. So this is the usual way that materials form in polycrystalline materials, as polycrystals, and you have grains and grain boundaries. And I think this is where material science comes from. We try to understand the structure at this length scale and try to manipulate the structure, try to get better properties or improve performance of the materials by trying to understand the structure at this scale. And for example, one variable that one can think of is the grain size, and the nanocrystalline materials are nothing but decreasing the grain size to a nanometer range. And there are other variables that you can play around with to get better properties for these materials. And one other property which people look at is how you can change the orientations. That is, when these grains that are single crystals have different orientations with respect to one lab reference frame, and the properties of crystals change with respect to which direction you look at. For example, the conductivity or other properties are, when they're anisotropic, you can have the property of the entire material depending upon the distribution of the orientations. You can tailor those properties and get better properties and desired properties. So the one way, so this is a design variable in material science, and there are actually experiments that can measure the grain orientations of any most samples, and the experimental advances also provide a way for material scientists to understand how these orientations are distributed. For example, we have diffraction techniques or a microscopy technique called orientation imaging microscopy that gives the orientation of individual grains. And so we have the experiments to determine the orientations, but we also need to parameterize the space to understand how the properties are related to the distribution. So obviously the orientations are nothing but rotations with respect to a reference frame. So the way we parameterize the orientations of the crystals is by looking at the rotation space, and there are different parameters that exist. Euler angles are the first one that were proposed, but there are other axis angle parameters or the unit quaternions that can be used to represent the orientations. And I'll be mostly using the quaternion parametrization for the rotation space. But it's the ability to actually parameterize the space and do analysis on the space that actually that helps enable material scientists to design better materials with different orientation distributions. So for example, one can describe statistics on the orientation space by using hyperspherical harmonics expansion on the rotation space, which can be used again to relate properties of the material to the distribution functions. So the idea here is to find these design variables that can be used to better the properties of the material. And as I was saying, the polycrystalline materials have grains and boundaries as well. And I'll be talking about the grain boundaries, but the topological analysis part, at least in this project, where it comes from is, again, in trying to understand where the symmetries in the grain orientations play a role. So the orientation space, even though it's equivalent to the rotation space, because of the symmetries, it's the quotient space of the rotation space. So for example, if we have a C2 point group symmetry, we say that we take, for example, a grain that we measure, and now one can fix a crystal axis on that grain and measure the orientation. But because it has the C2 symmetry, you could either think of it as rotating it by 180 or by fixing the crystal frame that is at a 180 degrees apart, and you could get another orientation measure, but both belong to the same crystal orientation, and hence they're equivalent. So you say that the rotation space is the orientation space for the C2 point group symmetry crystals is the quotient space with the C2 point group, or for any general point group is the quotient space with the point group symmetry. So my objective here is to try and understand similar variables for grain boundaries, which are again defects in the polycrystal materials and one that can be designed to get better properties. And there are various number of properties that can be improved by understanding the distributions of grain boundary parameters. So what are grain boundary parameters? This is the experimental advances in the material science community, that because of the spatial orientation mapping in 3D, they can now reconstruct real crystalline samples, and they can measure the grain boundary parameters too. And what do I mean by the grain boundary parameters?
That was an actual experimental picture of a crystal?
It is reconstructed, but it is experimental. So there was some correction done. There was some, I think, smoothing of the grains and stuff, but it's still experimental. So similar to how we had the rotation space for the orientations, we also have geometrical parameters that can characterize this grain boundaries. And the way we think about it is we want to bring two grains together, and we want to construct a boundary in here. So the first step is we misorient them, which is a rotation, and then one can translate the lattices by a certain amount. And then you have to pick a boundary normal, which defines the shape of the boundary. So there's a normal vector, and then you can move the boundary normal in the lattice. But the relative translation and the boundary position are more of microscopic parameters that people think that are relaxed in general. So you mostly care about the macroscopic, the misorientation, and the boundary normal vectors describing the grain boundary. So we have this geometrical characterization of each boundary, but we really want to use these parameters space to relate properties of the materials to the distributions of grain boundaries. And we haven't been able to do it just because we are not able to understand this high dimensional space, and mainly because there are also these other symmetries that I'll be talking about that are involved in the space. But that is a complete grain boundary space. So to understand this complete grain boundary space, as I said, there are two aspects to it. There's a misorientation aspect, and then there's a boundary inclination aspect. And most of the talk I'll be concentrating on the misorientation space that we try to understand, and try to understand how these symmetries play a role. And in a way, what we thought is the best way to understand the misorientation space is to try and represent them using colors. So I'll be talking about representing the misorientation space first, and if time permits, we'll be talking about the complete boundary space. So this again is an experimental sample with different grain boundaries on it. And the usual way that people represent this information is either they color it with respect to the angle of misorientation. So you have lost the axis misorientation information in general. Or the way they color it is whether they're these special cases that you observe in misorientation. So they color it by the special cases and the general cases, again, which is discretized. And this is mainly because we observed that they could not represent the entire misorientation information using colors, and we wanted to just do that because that's the most intuitive way to understand the space. Just color it so that each misorientation can be uniquely colored by a color, and it can be continuously colored as well, so that you can see the difference in misorientations by difference in colors.
So there's a three-dimensional set of misorientation.
Mm-hmm.
There's also a three-dimensional space of colors.
Yep.
Three receptors, and that's so that's what you mean by coloring.
Yep. Yep. So, yep, I'll be mostly talking about the representations or the coloring of the grain boundaries, and if time permits, maybe the complete grain boundary space and the problem of the complete grain boundary space. So as you just said, we have this rotation space that we represent as a 3D parametric ball. Each point so this is basically a 3D projection of the quaternion three-sphere, and each point in the parametric ball represents a rotation by where the unit vector is parallel to the axis of rotation, and the magnitude of the unit vector is proportional to the sine of the angle of rotation. And we have three independent parameters, and we want to color them with the color space, which also has three independent parameters. And the first approach, at least for me, was to directly map the points in the rotation space to the points in the color space. But obviously, it cannot be done because the connectivity of the rotation space is such that the points on the top of the surface, the diametrically opposite points, represent the same rotation because the rotations of pi along axis A and rotation of pi along the negative of that axis represent the same rotation, and by just fitting it to the color space wouldn't work. So this is probably the reason why people don't color the grain orientations and misorientations. And but we studied the case of 2D orientations and misorientations, which I'll be talking about, and that kind of pointed the way towards understanding how the symmetries change the topology of the space so that we could probably color it. And as I said, the topology of the rotation space is different from the color space, that you cannot just continuously map them. And the rotation space embeds in 5-dimensional Euclidean space, and the color space is just in the 3-dimensional Euclidean space. So the coloring of the rotation space wasn't possible, but the misorientation space I will be talking just now in a little bit is that we have symmetries in the space, and how does the symmetries affect the topology. So I'll be talking about the rotational symmetries in the crystals as they affected the grain, the topology of the orientation space, also act in a way, and we want to see how they affect the topology in the misorientation space. So the first part is the rotation symmetries, and I just want to show a small picture visualization where if you have two grains that have a misorientation of, let's say, 11 pi by 6, and this has a twofold rotational symmetry, each grain. You could see that by choosing your axis in a different way, or by rotating the grain on top by pi, you could get another misorientation. But you could also rotate the reference grain by pi, and that acts in a different way. So you have two symmetries for the blue grain and then two symmetries for the red grain, and you would end up with 4 different representations. So you have, so in 2D and 3D, the equivalence relations would be shown as such. But in grain boundaries, I just showed that as 2 red and blue grains, but they're actually the same phase, so you cannot actually distinguish between each other. So there's an intermediate step where you have to choose what is the reference grain or the reference axis. So you could choose one of them as the reference axis, and you would get M as your misorientation, and you could choose the other one, and you would get M inverse as your misorientation, and they're physically the same system, so they're equivalent misorientations, and this is what we call as grain exchange symmetry. So for the misorientation space, you have the symmetries because of the point group symmetry of the crystals, and there's an additional symmetry which we call as the grain exchange symmetry, which is because we cannot choose the reference frame directly. So as I said, we kind of try to first look at the 2D rotation space, which is nothing but the SO2 group that is homeomorphic to the one circle, and we do need 2 variables to color it continuously. But when we apply the grain exchange symmetry for the 2D rotations, the symmetry is as though the omega is equivalent to 2 pi minus omega, and that equivalence relation is as if you have a mirror line along the circle, and you could actually now use just one color variable to color it. So this was the idea that applying symmetries would reduce the dimensions of the misorientation space, and one could color it. So we first started by looking at the orientation space. As I just said, it's the quotient space of the rotation space, and the way at least I try to understand the topology of these systems is by picking. So when we apply these symmetries, the space is partitioned into equivalence classes, and we try to. So we have, at least in the quaternion parametrizations, we have one parameter Q0, Q1, Q2, Q3 equivalent to the quaternion rotated by a twofold rotation. That's Q3 negative Q2, Q1 negative Q naught. And we try to pick one representative of these equivalence classes so that we build what's called as a fundamental zone. And the property is such that any point inside the fundamental zone uniquely is a unique representative, but on the surfaces you have symmetries. And by trying to understand these symmetries, I was trying to understand the topology of the space. So at least for the
fundamental zone, you pick one element from each equivalence class.
Yep.
And you're trying to construct some continuous space that's connected to the identity. Is that what you pick?
out here, yes, that's connected to the identity. I picked the representative that has the minimum rotation angle. Yep. So the rotation space has this connectivity that the diametrically opposite points are connected. For the C2 fundamental zone, if you any point on the surface of this egg-shaped fundamental zone has an equivalent point that's as though you rotate the point by 90 degrees and then you come out of the negative z. So it's actually Q1, Q2 is equivalent to minus Q2, Q1, which is a rotation of 90 degrees, and Q3 goes to minus Q3. So I was trying to look up on literature where you would find spaces like this, and I found that these are actually length spaces. So you have the way length spaces are defined, the LPQ at least, is that you have a solid disk, three disks, and on the surfaces there are these equivalence relations that says any point on the surface, if it's an LPQ space, you would rotate it by an angle 2 pi q by p along the z-axis, and you would reflect it to the negative z, and those are the identifications. So at least for the C2 rotation space, you have a rotation by 90, and it's reflected to the negative z. So this happens for the orientation spaces of all the cyclic point groups. They're rotated by a certain point, a certain angle, and they're reflected to the negative z is the identification on the surface. So the orientation space of C1, where there's no point group, no symmetry, it's the rotation space, which is equivalent to L21. And for any OCn, it turns out to be L2n and 1. And for other point groups, for example, if the crystal has octahedral point group symmetry, the fundamental domain or the fundamental zone looks, for example, like this, and it has connectivities on the surface they look complicated enough, but they all seem to fall under this category called spherical three manifolds. So the way the spherical three manifold is defined is the three sphere acted upon by a finite subgroup, but the condition being it's a free action or a properly discontinuous action. And in that case, we have, and if we impose those equivalence conditions by the action of this group, you get a spherical three manifold. And I went in and checked for all the point groups of the 11 crystallographic point groups, and they do turn out to be a properly discontinuous action. You cannot, the way it's defined. So one intermediate step is to find what's the analogous group action from SO4 that's related to the group action on SO3. And we use this property that the quotient space of SO4 by the group identity and negative of that identity has this, is isomorphic to SO3 cross SO3. So we could find the group from SO4 that acts on SO3 that's equivalent to the group that acts on SO3. So I just call it G star, and all these orientation spaces fall under the spherical three manifolds, and they have the embedding dimension, which is a minimum of 5. So clearly we cannot color the orientation spaces. So what about the?
Do you mean
Sorry.
dihedral group?
Sorry.
Those D's are dihedral.
Yep.
Yeah, star
Yeah.
means it's the binary dihedral group. That's the
Mm-hmm.
standard word for that.
The binary dihedral.
The inverse image in S3 is just called the binary dihedral. Binary.
And T is tetrahedral, and O is octahedral.
Yep. So we move on to the misorientation spaces. So the misorientation space has the rotational symmetries and the grain exchange symmetry. The first step is apply the grain exchange symmetry. So I have the rotation space in this parametric ball. The grain exchange symmetry says that in this parametric ball, any point, any vector q is identified to a vector negative q. So that's q is q inverse, and this is the symmetry. And again, I pick a fundamental zone such that the q3 component is greater than 0. So I have a hemispherical solid, and for the z equals 0 plane, in that plane there are identifications where the xy coordinate is identified to negative x, negative y. So the way that I look at fundamental group is to draw a path in the space and try to shrink it continuously to a single point. And this construction is for the rotation space, and one could see that this cannot be done, and it's actually the rotation space has a non-trivial fundamental group. But for this misorientation space that I just showed, we could draw these paths, and every path can be actually continuously deformed to a single point. And it's actually the C1 misorientation space could be seen as a cone space of RP2, and as you might already know, cone spaces are simply connected. So there's one which I see it as a simplification in the topology at least, that the rotation space when the grain exchange symmetry is applied turns into a simply connected space. Let's try to apply the symmetries as well for the C2, the twofold rotational point group. So first, just the rotational symmetries. So this is the orientation space, that's SO3 by C2. But the way you're applying the group operations of C2 from the left and the right, so I can denote it as X. And the fundamental zone for when the rotational symmetries are applied are as if you cut a half of it, and because of the relation as that's shown under this picture, basically the fundamental zone is half of the orientation space. And again, once I have the fundamental zone, I try to look at what the connectivities on the surfaces are. There is this, any point on the surface is still rotated by 90 degrees and is identified to a point in the negative z. There's also on the surface c equal to 0, it's as if there's a mirror line. Any point that has a negative b coordinate is equivalent to a positive b coordinate just on the plane c equal to 0.
So by the surface, you mean you've got this thing which is sort of flat on the bottom and ball-shaped on the top, and then by the surface you mean this top ball shape.
Top ball shape, and
you're identifying points up there.
yep.
Well, and also
On the flat surface in this case. On the ball shape, there's that the lens shape symmetry. On the flat surface, there's a symmetry as if there's a mirror line on this flat. So I just color it as blue because I have my surfaces that have a mirror-like symmetry as blue. And what I try to do is deform it because these surfaces are is as if there's a mirror line along on that surface. I could actually merge those two faces because it's as if they're identified, and I do it in the steps. And what you see here is you have the egg-like shape, but the points now on the surface are identified such that the difference in angle between them is 180 degrees, which was the case in rotation space. the rotation space actually looks like this, where you have a solid ball and diametrically opposite points are identified. So in this case, when the rotational symmetries are applied, just the rotational symmetries, the misorientation space is homeomorphic to the rotation space. And when I apply my grain exchange symmetry, it just, again, as if you're applying grain exchange symmetry to SO3, and that was the initial C1 point group misorientation space. That was the cone space of RP2 that was simply connected. And we find this for the 6 point groups, that they're all topologically equivalent, and they're simply connected spaces. Now I'll talk about the...
Topologically equivalent, you mean they're all a cone over RP2?
They're all cone of RP2. But so I've shown 6 point groups. There are 5 other point groups that can exist, and I'll show an example of the octahedral point group. What happens in that case? So this is the orientation space that I showed, fundamental zone of the orientation space. The misorientation fundamental zone, when just the rotational symmetries are applied, looks somewhat like this. It's this prism kind of a shape. And again, I'm trying to look at what are the symmetries on these surfaces. So I have A, B, D, G, and the points that are shown there are identified. It's as if there's a mirror line along AD. And the same happens to the surface BCED. There's a mirror line along CD. And for the surface DGFE, there's a mirror line along FD, and you have points that are identified as such. And for the top surface, there's a mirror line along this is the bottom surface. So ABCO, there's a mirror line along AB, and for the top surface, it's as if there's a mirror line along AF. So it's basically any point on the surface, if has a mirror line on that surface, and it's identified to the other half on the other half. So the way we look at it is first cut it into 2 pieces, and so any point on the surface of this half has another point on the surface identical on this half. And I'll show you in a minute how each half can actually be deformed such that it turns into I show a cone here, but it's equivalent to a 3-disk. So what we do is we have this one surface that has a mirror symmetry on itself on the same surface. So we collapse that surface, and we basically end up with 2 3-disks, with any point on that surface has an equivalent point on the surface of the other 3 disks. So it's basically a 3-sphere. So, sorry?
3 ball.
3 ball, yes. Yeah, 2 3 balls, and they have.
But you glue them together on the surface.
You glue them together on the surface, so it's a 3-sphere.
Oh.
So for the other 5 point groups, we see that when the rotational symmetries are applied, it's just the 3-sphere. It's not so 3 as in the previous first 6. And after you apply the grain exchange symmetry, the grain exchange symmetry actually just restricts the fundamental zone to 1/2 of it. So you see that it's just a 3 ball. So at least for these 5 point groups, they are the misorientation spaces are homeomorphic to a 3 ball, which is actually what we wanted when we started and tried to color them.
Could we go back and get the definition of misorientation space again?
Misorientation space?
Yeah. All the way back, or can you just say it? I mean, it sounds like you're talking about
Could try to go in there and.
spherical orbifolds or something. Covered
Yes,
with
it is. It is an orbifol. It's a double.
So 3 sphere divided by group which isn't anything freely. So.
That's right.
Yep.
Yeah, okay, I see. So the grain exchange symmetry
just going to skip all of that.
But now,
You know where there's a list, another place to look this stuff up then, I think, is this, there's various places, but like, one of Thurston's students has a big list of all spherical orbifolds, Bill Dunbar or something.
oh,
I forget where it's been published. It's got
there's a
descriptions
student of
of
mine
these
at one
things.
point.
What?
There was a student of mine at one point.
Or somebody else did it.
No, he was an undergraduate student.
Oh, Bill Dunbar, you know who he is.
But, wait, so in the end, you gave us
So,
all the answers, but could you summarize what you said? Some of them are a cone over RP2, at least one of them is a 3-sphere, and some of them are 3 disks.
So
You
I'll-
have a slide
I'll
that
just do
summarizes
that, yeah.
the whole
but
thing?
then you have to
Okay.
have, I mean, you have these other places where the, sort of have orbifold, cone angles or something. I mean, you have on the I mean,
Yeah, he's dropping the orbifold structure.
Right.
He's just looking at the quotient space.
there's some sort of knot or lines or something in there that, where there's some singularity, there's a cone angle around some interval, right?
For these first,
There's some special lines. No, there's the mirrors which show up as the boundary of the D3 of the 3 disk, but then there's some. There's some, like in the 3-sphere, you're going to have some knot inside the 3-sphere or something.
so I'm not sure if I got it correctly, but at least in this,
Where you're folding things up.
Yep.
That thing is a
I've
special line or something.
yeah, there's this line AD where I actually fold it up.
Right.
So yeah, that should be the special line. That line is in both halves, and I fold it around that line to get the D3. But yeah, to summarize, so there are 11 crystallographic point groups. When you apply just the rotational symmetries, the first 6 have an equivalent structure of the rotation space, and the last 5 are equivalent to the 3-sphere. And when I apply the grain exchange symmetry, I find that the last 5 spaces can actually be mapped to a color space. So,
Wait.
sorry.
So the last 5 are a 3 disk, and the first, the
6.
green ones are the cone over RP2.
Mm-hmm. Yep. So at least for me, it's not completely clear what the distinction is. I see that the cyclic groups end up in the cone spaces. There's this one dihedral group that also belongs to, that has this property that after all the symmetries, you would see the cone space, but the rest 5 are actually can be embedded in R3. So if we go back again to coloring the grain boundaries, these are the previous existing schemes, and then as I said, I would show how I kind of fold it. So I have this small animation that I take the misorientation space and I fold on that mirror surface to get the sequence where we deform it to form a 3-ball. So, and then we do the coloring, and we have this pretty picture for grain boundaries, where each grain boundary is colored according to its misorientation. It is an embedding, so it's continuous and one-to-one. So we try to have intuitive features that can be inferred from this coloring scheme. For example, distance between the misorientations in these grain boundaries.
The space of color has these special points like white and black and so on. Do you map it in such a way that
I-
those go to interesting things?
We try to. So white corresponds to 0 misorientation. So it's an identity. And we try to increase the contrast as the misorientation angle increases. We do not exactly map it, but that's the idea. And try to get, so the misorientations along 1, 0, 0, 1, 1, 0, and 1, 1, 1, these three axes are somewhat special, so we try to have red, green, and blue along those lines.
So the whole picture is colored then?
All the grain boundaries are.
Even
You could have the whole picture colored too. Yes.
if white.
Yep.
Well, but what he's
Yep.
doing is he has pixels, and each pixel corresponds to some volume element with an orientation, and then he's coloring the boundaries between the pixels.
Yep.
According to the operation to go from one orientation to a neighboring one.
Right. But saying exactly to say that the entire picture is colored.
Yes. The boundaries between
All the pixels. Yep.
It's just most of them are white.
So, let's see. There's a three-dimensional structure. I'm looking at a two-dimensional picture. What's going on? This picture on the left is a two-dimensional picture.
Okay. Oh,
Is it a slice or is
it
it
is a slice. It is a slice. It's a.
It's a flat slice
Mhm.
through the thing.
Yep.
And this is experimental data?
Yep.
And it's
Yes.
wait. That I'm not understanding. Here appears to be a line. Here's a grain. Here's a grain. Here's a line between it. The colors seem to be changing. Why would that?
So the sample that, at least this sample, it was heavily worked. So you have even within the grains, within a single grain that we define as a single grain, there are small orientation changes.
There's a lot of stress.
Yes.
Internal stress.
Yes. And
You can see that in some of these grains, these light lines that kind of begin and then end in the middle of one of these white regions.
so there are these big grains that have
Yeah.
very light grain boundaries that's actually an effect because of the interior strain, the strain in the grain.
So the fact that all of this isn't very dense, that's that the misorientation is smaller.
Mm-hmm.
And so there's some question about what you define as a grain.
Right.
Right, but
Yep. Yep. So, as we just said, we try to get some intuitive features out of the coloring. For example, as pointed, there are some variations in the misorientation in a grain that are normally not captured in the previous coloring schemes, but we can do that now because of a continuous coloring scheme. Or
Right, the guy on the right was a previous coloring.
yes, it's just it was general high angle boundary, just colored black, that we would not know what the misorientation is usually, but here we can actually compare it with the legend and get the misorientation information directly.
the sigma 3, the sigma 9, and the sigma 27, what are those?
So those are the one that we color as red, blue, and green. They have in the material there are low energy boundaries because they have special orientation relationships. For example, sigma 3 is a twin boundary. It's called a twin boundary, and the misorientation is such that when the grains overlap, they form this low energy structure in the interface. So from a material science point of view, those boundaries are of more interest, so you color them in different ways. But again, we end up discretizing when we do this characterization. We could still see from this coloring scheme, it was mapped to a dark blue color, so we could still get all those features, but we also want to see how different, for example, out here at a triple junction, how different these boundaries are from each other in the misorientation space, and we would want to use just the colors to infer such an information. So the summary for the coloring schemes is we have misorientation spaces. As I said, I look at the grain exchange symmetry, somehow simplifying the topology, and for the five 5 of the 11 crystallographic point groups can actually be colored because they can be mapped into R3. And depending upon the time constraints, I would want to talk a little bit about the complete 5-parameter space. That is, you have a boundary, as I said, is characterized not just by the misorientation, but also the inclination vector, the normal that lies along the plane. And the usual way to see this, so when we talk about both the misorientation and the inclination, we would like to see these grains in their usual 3-dimensional shape, and the boundary is normally triangulated, and each mesh has a misorientation and a boundary normal. And it's thought that the space of this parameters is the product of the misorientation and the two-sphere. And similar symmetries exist. I'm not going to show what each is, but because of the rotational symmetries you have for the complete 5-parameter space, you have the usual previous symmetries for the misorientation and also for the boundary normal. And the grain exchange symmetry, which also somewhat looks like this, where M and N correspond to M inverse, and M inverse, the normal vector looked from the different reference frame.
So on the grain exchange, you change the normal vector and you switch the two orientations.
Mm-hmm. Yep. And so there's one more aspect that falls into place when we look at the normal and the misorientation, is the fact that when there's no misorientation between two grains, it's a 0 misorientation, but the parameter space itself, because if we, for example, if you look at it as a product space, at the 0 misorientation it has this 2-sphere degrees of freedom, but in the physical space it's actually just one point that has no boundary. So we collapse the boundary degrees of freedom for the 0 misorientation, and we call it as a boundary singularity in the space. It's called the no boundary singularity. So if we look at all the complete 5-parameter space, we have the rotational symmetries, the grain exchange symmetry, and then there's a no boundary singularity, which I think actually complicates the space that one is not able to do analysis on this 5-parameter space. So the first step I tried to do in trying to understand how the space looks is first simplify this grain exchange symmetry that looks somewhat complicated, because if I look at, if I think of this product space, every misorientation has a 2-sphere attached to it. And this relation says that if M has a 2-sphere attached to it and M inverse has another 2-sphere attached to it, these two are related by this rotation M inverse. And this M inverse could be anything depending upon what M is. And so this rotation by which they're related changes from point to point, and that equivalence relation seemed complicated. So I tried to do a mapping to different parameters where I could at least remove some of the dependence on M, and this has to be obviously homeomorphic, but we could do this mapping to MR space, where when we transform it accordingly, you see that now the 2-sphere attached to M is related to another 2-sphere attached to M inverse, such that if you draw a plane perpendicular to the axis that defines the misorientation, so for example, if M is defined as a misorientation of angle omega around an axis A. So if you draw a plane perpendicular to axis A in that 2-sphere, you could reflect that 2-sphere in that plane, and that's the relation between the 2 spheres. So if you reflect a 2-sphere attached to M along a plane that's perpendicular to axis A, you would get the 2-sphere, that you would get the identification to the 2-sphere sitting at M inverse. So in this case, the equivalence relation still is dependent on M from the axis, but the angle dependence is removed. So that's a small simplification that we tried to do that actually helps in the 2-dimensional case, because the 2-dimensional systems, the misorientation is only along the z-axis. So, for example, if we want to look at the two-dimensional complete boundary space, so there's a misorientation that belongs to the circle, and then the boundary inclination also can take points on the circle. So in the two-dimensional systems, the boundary space is usually thought to be belonging to the torus. But you have the no boundary singularity turns out as a pinch in the torus, because for one of the for zero misorientation, you have to collapse the boundary degrees of freedom. And the other way to look at it is just pull it apart, and then you have a suspension space on the circle. And it's a suspension space such that the top and the bottom points are identified. And on that, we apply the grain exchange symmetry, which I just talked about, which says that any circle attached to a misorientation is equivalent to M inverse and another circle reflected along the z-axis, which is the same circle because it lies in the plane. So it turns out that for the 2D systems, it's just a two-sphere with an equivalence relation as though there's a mirror plane in the z equal to 0 plane. So in some sense, we could do analysis on two-sphere with this equivalence relation and for the 2D boundary systems. For the 5-parameter space, for the 3D systems, we could look at it as a suspension space over the product of two spheres. So the misorientation has an angle of misorientation and a rotation axis A, and the boundary normal belongs to a two-sphere. The axis of misorientation belongs to a two-sphere, and then we could change the misorientation angle, and we could think of the axis and the boundary normal vector belonging to the product of two spheres, and at 0 and 2 pi misorientation, these has to collapse, so it looks like a suspension space. The trivial symmetry is something that we already know is just the antipodal relation on the three spheres, so something that needs to be added onto the suspension space. But if we look at the complete grain boundary space and parameterize as a suspension over two spheres, these are the equivalence relations that I would leave it on there, but this is the point to which I understand the complete grain boundary space.